Hello, I'm Matthijs Laro, and I do my graduation project for the Bachelor, for my Bachelor from Fontes. And here we have the measurement setup for measuring the performance of a flexible deck. This is a test PCB with on it the test chip. It's the flexible deck. The data to the flexible deck came from the FPGA. It's a Vertex 5 FPGA. It's one of the fastest FPGA this moment, and it's can generate generate data with high speed. The measurement devices are oscilloscope and spectrum analyzer. This is the clock generator which generates the clock signals for the FPGA PCB and the test PCB. The flexible duct test chip has 16 12-bit subducts inside, and with the 16 subducts it's possible to make 5 different output signals.
They show here, yes.
There is a 12-bit which is made with one deck, another 12-bit also one deck, 14 bits which can be made with 4 subdecks, a 13-bit for 2 subdecks, and a 15-bit for 8 subdecks. The digital data came from this FPGA PCB. It's a FPGA board, the ML550 from Xilinx. It's specially made for high-speed LVDS data. Here it's the FPGA, the Vertex 5, and it generates on this moment a sine wave. This sine wave with the buttons, the frequency of a sine wave and the amplitude of a sine wave can be
can be controlled.
Can be controlled, and the digital data came out this LVDS connector.
So where is the clock?
The clock came from the clock generator through the coax cable to the FPGA.
And then you get the data out?
Yes, then I get the data
through
out.
The blue cable?
Yes.
And with these buttons you can control the
frequency and the amplitude, and I can put the program on and off or reset it.
So now at the moment digital data comes from the DAC, from the FPGA, and goes to the DAC.
Yeah.
And now we are measuring the 14-bit out, I believe.
Yes, that's true.
So can we see something? Now this cable goes to the oscilloscope.
Yes. Now this is a 14-bit sine wave. The frequency we show can decrease and increase it. So
you increase the frequency by
press the button on the FPGA board. And also the amplitudes can be lower.
Okay.
And you can change the amplitudes also.
Can we see also this time information in the frequency domain?
Yes. The spectrum analyzer. Here we have the signal with the harmonic distortion. Yeah, this is the signal in frequency domain, and also change the amplitude.
Okay. Can you explain us what we are seeing at the moment in the spectrum analyzer?
This is the main frequency. It's the frequency of a sine wave, and the second, the third, and the fourth harmonic. Which also means it isn't a pure sine wave. Maybe I could show the harmonic distortion of this moment. We measure now the harmonic distortion, and we have a 2.1 megahertz signal, and at the second harmonic we have 62 decibels. And the FPGA, maybe it's better to show it on the computer. I don't know, can you see it? Yeah. In this there is a sine wave block, and this contains a lookup table to control the address speed to the sine block. I can the frequency.
Can adjust the frequency.
You can change the frequency, and on this moment through a shift register I change the amplitude of the sine wave and put it out with LVDS signal, and this block should do this. This is the schematic. It's all right in VHDL.
So behind each of these blocks is a VHDL code that you wrote?
Yes.
Okay.
And I put it in the FPGA by programming it, and you can program it, and it's
so you program it from here
to the FPGA.
To the FPGA, and then
we
measure.
Measure.